Welcome to Electron. In this example, we're going to show you why we actually call these the Markov chains. Why the word chains is because there's usually a chain of events associated with it. In the previous example, we showed you a simple transaction. We showed you the current state, a probability matrix, and the next state. For example, we had 3 stores. We had a certain number of customers going to each of the 3 stores. We had a probability that the customer would stay either in the same store or would go to another store the following week. We put that in a probability matrix of how we thought the people were going to move around from store to store or stay in the same store. And from that we could predict what the number of customers would be in the store the following week. But what if we want to know it for the 3rd week, and the 4th week, and the 5th week, and the 6th week, and so forth? Well, that's why we can do this transaction over and over and over again. As long as the probability matrix doesn't change, we can see where the customers will end up in the long run. What will be the end state of this particular situation? So the way that works is we have the initial state, we have the probability matrix, and we have the next state. So we're going to calculate state 1, which is based upon the probability matrix multiplied by the initial state. So we have the initial state, 40% going to store A, 24% of people going to store B, and 36% of people going to store C. And this was the probability matrix of where we thought that customers would go the following week. From that, we calculated that store A would now have 40.4% of all the customers, store B would have 31.6%, and store C would have 28%. So you can see how store A gained a few customers, store B gained a lot of customers, and store C lost a lot of customers. So let's see what happens the following week. So what we do is we take the state 1 and make that into the current state. And now we calculate state 2 by multiplying the probability matrix times this state matrix right here, which means we're going to multiply this times this, plus this times this, plus this times this, to come up with the new number of customers going to store A. So this becomes, and let me show you over here how that's calculated. So it's 0.8 times 0.404 plus 0.2 multiplied times 0.316 plus 0.1 multiplied times 0.28. There. So it's these two plus these two plus these two gives me the value for the first cell right over there. So let's go ahead and calculate and see what that is. So we get 0.8 times 0.404 plus 0.2 times 0.316 plus 0.1 times 0.28 equals, and we get 0.4144. So let me write that down. Where's my black pen? Right here. So this becomes 0.414, and I'm only going to keep 3 decimal places. There's no point in just carrying out too far. All right, next. Now we're going to multiply this row times this column. So it gives us 0.1 times 0.404 plus 0.7 times 0.316 plus 0.3 multiplied times 0.280. So again, the way that works, it's this times this, plus this times this, plus this times this. So you go horizontally here and vertically there. So let's calculate what that is equal to. So 0.1 times 0.404 plus 0.7 times 0.316 plus 0.3 times 0.28 equals, and we end up with, and let me get my black pen out. So this would be 0.346. All right, now next. So now we're going to multiply this row times this column, and we're going to get 0.1 times 0.404 plus 0.1 times 0.316 plus 0.6 times 0.28. All right, and that will give us the 3rd result. So 0.1 times 0.404 plus 0.1 times 0.316 plus 0.6 times 0.28 equals, and this will be 0.240. Now, you can see that this would be the number of customers attending store A, store B, store C as a percentage of the whole or as a fraction of the whole. If we now multiply that times the total number of customers, remember that we started out with A having, that would be 200 customers, B having 120 customers, and C having 180 customers. Let's see how that changed after 2 weeks. So we're going to go ahead and multiply each of these by 500 customers. Now, before we do that, just to make sure we didn't make a mistake, let's add all these numbers together because they better add up to 1 or somewhere we made a mistake. They look like they add up to 1, but let's just check. 0.414 plus 0.346 plus 0.24 equals, yes, they do. You add them up vertical like that, they add up to 1, so we're good. So that means that x2 in number of customers is equal to multiply 0.414 times the total number of 500 total customers. So 0.414 times 500 equals, that's 207 customers going to store A. 0.346 times 120. I'm sorry, take that back. So that would be 500 times 0.346 equals, that would be 173. And finally, 0.24 times 500 equals, that would be 120. So after 2 weeks, we can see that 207 people will be shopping at store A, 173 will be shopping at store B, 120 will be shopping at store C, and that is compared to where they started 2 weeks earlier. And of course, we can continue doing this time and time again. That's why we call it Markov chains. And eventually you will find that this typically will converge to a particular number. We'll come to a certain number of customers in each store. It will then stay at that number. And that's what will tend to converge to. And that's what typically happens in business, in nature, in science. These things will eventually converge if the probability matrix does not change. So again, that's why we call it chains. We'll show you a lot more examples of how to work with Markov chains.